Hi guys, my name's David and today I'm going to be talking to you guys about sets and set notation. So to begin, a set is a collection of objects or things that have two important properties that you must remember. Number one, they must be well defined. For example, if you told me that there was a set of things that you found interesting, I don't know what you find interesting. That's not rigorous and well defined, so therefore it can't be considered a set. Number two, there are no duplicates. Every object in a set must be distinct and unique. So here are some examples of sets that you might see in everyday math. Notice how every object in the set is enclosed in these curly braces. And I'm kind of tired of calling them objects, so each individual object in a set is called an element of that set. Furthermore, note how I give names to these sets. That's just so I don't confuse them with one another. Sets don't only have to have numbers in them, although that's what you usually find in math. For example, set C here has a shape or a picture of a stick figure, the number 72.1, and a picture of my good friend Ali Jaffrey. Some sets might be finite or infinite. For example, set B here starts off as 1, 2, and 3, and then the elements seem to just go on forever. Usually when a set is infinite, there is a noticeable pattern. Finally, set D is a set with no elements in it. That's a bit strange. However, that is a very important set, and we will call that set the empty set. Another way that people like to denote the empty set is a 0 with a slash going through it. Something else that I like to point out is that the elements in a set can be rearranged in any order, and it would still be the same set. Rearranging elements in a set gets a bit more complicated in infinite sets, but we'll talk about that more later. Now that we've gotten the basic definition of a set out of the way, let's talk about some operations that we can perform on sets and some notation. Number one, the length of a set. To denote this, we usually put two vertical bars around the name of the set, and to get the size, we just count how many elements are in a set. So for set A, we can easily count that there are 3 elements in set, and for set C, there are 1, 2 elements in set C. For set B, on the other hand, it's an infinite set that goes on forever, so we don't know what the actual size of set B is. We cannot conclude the length of set B. Number 2, is an element of. So this weird looking E is used to describe when an element is in a set or not. If you're having a hard time remembering the E, you can think of the E standing for exists, or the keyword element. Let me show you how it's used. Alright, so I wrote some examples, all of which are true. Hopefully they're not too small. But all you do is you put an element at the very beginning, and you say that it is an element, or it exists in a particular set. Now, if you want to say that something is not an element of, or does not exist in a particular set, you just put a slash through it. And let me just give you an example here. 5 does not exist, or is not an element of set A. Number 3, is a subset of, or is contained in. So the next symbol or piece of notation is this C with a line underneath it. Whenever all the elements in one set are also in another, then we say that that first set is a subset of the other one, or contained. That's a good way to remember the big C over here. Let me give you an example. So set C here has the elements 1 and 3, and the set A has the elements 1, 2, and 3. Because all the elements in set C are in set A, we can say that set C is a subset of set A, or C is contained in A. However, the contrary is not true. The number 2 is not in the set C, so we're going to say that A is not a subset of C, and that is denoted with a slash going through the horizontal bar under the C. Now before I move on, I'd like to talk about some really important properties about subsets. Do you remember the empty set? Well, we're going back to it now. The empty set is a subset of every set in the whole universe. In fact, it's even a subset of itself. Furthermore, we can expand onto that and say that every set is a subset of itself. Now, this may be a bit of a shock to you, and I could mathematically prove it to you rigorously on why these are true, but that's a bit too complicated. So just take these for granted and I'll prove them to you in a later video. Number 4, the union and intersection of sets and set differences. So the union of a particular set of sets, denoted with this U, are all the elements that are either in one set or another. So the union of set A and C should be 1, 2, 3, 1, and 3, right? As those are all the elements in those two sets. However, remember what I told you about sets not being able to have duplicate elements? This is actually wrong. Let me fix that. That's the correct answer. So the intersection of sets is different from the union. It is a set containing only the elements that are in each of these sets. They must be the same. As you can see, set A and set C share the elements 1 and 3. They're both in each of those sets. So the intersection of set A and C are 1 and 3. Back in high school, the way I used to remember this is that it kind of looks like an N, right? So this is a bit far-fetched, but it kind of spells out and. This is a set containing elements in one set and another. Finally, set difference, a little slash, is a set containing elements that are in one set but not in the other. And the way you position the sets are actually different. These are two completely different sets. Now, in the union and intersection, it didn't matter. However, for set difference, it does. So this first one over here is asking for all the elements in set A, but not C. And we can see that the only element in A that's not in C is 2. However, in the set difference for all the elements in C and not A, there's actually nothing, because C is a subset of A. So the answer is just the empty set. So finally, we're going to talk about important sets of numbers that you'll definitely see throughout your math careers. First are the set of natural numbers. Now these are the counting numbers that you've seen throughout your life, first in kindergarten, starting at 0. Now there is debate on whether or not 0 is a natural number, but I'm not going to get myself into that. Second one are the set of integers. Basically, it is a set of all whole numbers or naturals and their negatives. We have the set of quotients, which are the set of all fractions and quotients of all integers. We have the algebraic reals. They contain all roots of numbers that you can't make with quotients. And finally, we have the set of real numbers, which is basically any number you can think of. All possible decimal expansions, all numbers on the continuous number line with no gaps. One cool thing that you should know: each of these sets, in this order, are subsets of each other. So that is it for sets and set notation. I put some questions up on the board earlier to make sure you have a good understanding and grasp of the content that I taught. Please attempt them on your own, and I put some answers in the description just so you can verify your answers. Just don't cheat. If you would like some additional resources on the stuff I taught, maybe in case something wasn't clear enough, I have put some additional links in the description so you can check them out. Next announcement, if you have any suggestions on future content that I could teach, there is like a little suggestion box, a URL in the description that I've also put as well. And if you have any questions pertaining to the stuff that I just taught, please leave them in the comment section and I will happily answer them for you to my best knowledge. That does it for me. Thanks for watching, and I'll see you guys in the next video.